All right, so today we're going to be looking at this topic called electromagnetism. Okay, and when we talk about electromagnetism, we realize that in this chapter, okay, actually, this is a very important chapter for us lah in our lives. More important actually than chapter 3. Well, chapter 3 kan is just electricity kan. But electromagnetism is really the foundation of many technology that we have today. Okay, for example, the fan that is right next to me lah. Okay, the fan that is right next to me is an example of electromagnetism at work. Okay, how many of you have ever actually asked yourself lah? Okay, like, oh yeah, kenapa kalau sorry hold on how many of you have actually asked yourselves like, kenapa kalau bila saya pasang, how is it now that when I turn on the fan can the bila can spin? And most of us, we don't think about it because we know that the moment we turn on, the fan can spin. Every time we have done an electricity experiment, kita pasang current, bahkan the light bulb lights up. Okay, so what is that extra thing? What is that extra step that you need to make the fan spin? Because electricity cannot make things move. Electricity can only provide current, okay, to light things up, to menghidupkan benda lah. Tapi untuk menggerakkan benda, for example this fan lah, okay, maybe the fan boleh hidup tau, tetapi untuk menggerakkannya, to make it move, okay, is another extra step. And this is where electromagnetism comes in. And a lot of the technology we use today is really based on everything that you're about to learn in this chapter. Okay, which is why this is one of my most favorite chapters, because we see each and every day more and more technologies being developed based on this, based on the things that you are learning in this chapter, okay, which is electromagnetism. All right, so the first thing that we need to talk about is this idea of the force on a current carrying conductor in a magnetic field. Now there's a lot of words lah, okay, in this subtopic. Force on the current carrying conductor in the magnetic field. Last time when I used to study this I really hated this subtopic because there's so many words. It's like, apa ini? And usually it's like, okay, for example, when you're in chapter 2 from 4, right, you're like, the subtopic is inertia. So you know that it's about inertia. Impulsive force. So you know it's about impulsive. Very short subtopics. No? But this one is such a long subtopic, and there's really no other way. Okay lah, fine, there is another way lah, but there is really no other way to explain this subtopic. Okay, so there are 3 things that we need to talk about when we talk about this particular subtopic. The first one is this word called the force. Okay, a force is always produced. Okay, so this is the one thing. Second thing is this one, the current carrying conductor, the CCC. Okay, force on a current carrying conductor means you have a conductor, a wire, okay, a piece of metal, anything that conducts electricity lah, yang membawa arus, that is carrying a current. Okay, that is what current carrying conductor means. Okay, conductor pembawa arus. Okay, yes, when I say conductor means conductor yang membawa current lah, okay, not the conductor bus lah, okay, please. So current carrying conductor is a conductor yang sedang membawa arus. It's a wire that is carrying current, okay, and it is not carrying current in any situation. No. It's a very specific situation. Okay, it is carrying a current. It's carrying a current in a magnetic field. Okay, so I want us first to dissect this subtopic. This is a force yang terhasil. Okay, terhasil oleh apa? Terhasil oleh a current carrying conductor. Kamu ada satu, conductor, satu wire yang sedang membawa arus dan terletak inside a magnetic field. And when you look at this subtopic you know that there are 3 things that are happening at the same time. Force, current, magnetic field. Have this in mind when we dive into this subtopic. This will take us about 3 classes lah, I think. Okay, 3 kelas mungkin saya dapat habis lah. Okay, kita mau mencari apa yang menyebabkan the force, daya, apa yang menyebabkan pergerakan. Okay, for example, the fan. Okay, the fan next to me. When it moves, okay, it is moving because there is a force on it. Think about it. Force always changes directions. Force always makes things move, makes things stop. Okay, so the fan is moving because somewhere inside the fan, there is a wire yang sedang membawa arus. Why is it bringing current? Because we provide electricity to it. And at the same time, this wire that is in the conductor, this wire that is carrying the current is inside a magnetic field. Means somewhere in this fan, okay, sorry, I don't know if you can see the fan now, but somewhere in this fan, there is a magnet. Okay, there is a magnet. Even in all your fans, every single fan that is moving in your house, anything that spins, okay, kamu punya blender, even your oven, okay, anything that has a fan, basic stuff lah, fan will have a magnet inside. Okay, we don't think about this now because all we just see is the fan only, pasang fan macam tu. But when we look deeper into it, we're like, oh, okay, the fan is moving because there's a force. And there's a force because we provide current, and the current must be in a magnetic field. So this subtopic is to see how the current and the magnetic field interact to produce a force. I repeat, this subtopic is about macam mana arus dan magnetic field bergabung untuk menghasilkan satu daya. Okay, have this in mind when we are talking about this. Okay, so this is, as I said just now, this is a fan, okay, that is driven by an alternating current. Okay, so our question, the question that I need you to answer at the end of this all is how does this electric motor work? Okay, when we dismantle the fan, we find that there's this component inside the fan, which is basically the butt of the fan lah. Okay, yang di belakang ini kan. Sorry, I don't know if you can see this fan lah. But the back of the fan. Okay, atau kalau if it is a, the ceiling fan, the thing that is holding the three blades together, that shape of the cone thing. Okay, sorry lah, I don't know, my fan is this the shape of the cone. There is a motor inside there. Okay, there is a motor, and the function of the motor is to provide movement. Just like a motorcycle. Man, you ride on a motorcycle because the motorcycle, provides movement. Dia akan menyebabkan pergerakan. Nama pun motor. Okay, so another use of this one is this electric train. The electric trains that we have in Malaysia, okay, well, actually in West Malaysia lah, okay, even the bullet train that is very popular in Japan, okay, Japan, Germany, they have all these things called the bullet train. Okay, it uses a large electric motor, okay, while a smartphone, the phone, your phone, okay, there is a motor inside there also. Think about another place where you have your motor. The very laptop that you are watching this Google Meet from, okay, also has a motor. How many of you, if you overwork your laptop, then suddenly your laptop becomes like Boeing 747, the fan, okay, there is a motor somewhere inside your laptop. There is a motor somewhere inside, inside your phone. The function of most electric motors is based on this, the effect of a current carrying conductor in the magnetic field. There is current flowing, and somewhere in there is a magnet, okay, that provides a magnetic field. Okay, so today what we want to do is this one. We want to see how the effect works. Okay, and basically how it works, okay, take a look at this video. So we have this setup over here. Okay, there's these two magnets which we call the magnetar magnets. Okay, please let me know if you can't see the slide now. Okay, there's these two magnets that are called the magnetar magnets. Okay, magnetar is just a material. Okay, I think it's a form of alloy lah. Okay, but because of the way the two magnets are positioned, one of the magnets is a north pole and another of the magnets is a south pole. Satu adalah kutub utara dan satu lagi adalah kutub selatan. Okay, we're not interested in that yet. Okay, not yet. Okay, not yet. But on top of that, you have these two copper rods. Okay, yang disambung. Okay, the two copper rods is disambung, and then there's another copper rod that is not well. Oh, sorry. There's another copper wire over here lah. Okay, I hope that you can see over here. There's a wire over here. Okay, so since all these three are connected now, obviously when I turn on the switch, there is going to be current flow. Maybe current flow here, here, here. Okay, atau it can flow the other way lah. Maybe current flow here, here, and here. It is touching. Okay, it is touching means ada current flow lah. Kan macam kalau kau main kejar-kejar kan, I don't know, last time when you play kejar-kejar kan, there's this current thing kan. Asal kamu bersentuh, walaupun kau punya 2 jari saja bersentuh kan, terus ada current begitu kan. Last time lah when we play kejar-kejar. Okay, sorry lah, okay fine. I'm the what generation am I? I'm Gen X kan. Okay fine, so Gen X generation kami main current ini dulu. Okay, kalau main kejar-kejar. So these things are touching, although they are not one wire. Okay, they are not one wire, but these 3 wires, the 2 rods and the copper wire are actually touching. And so when we turn on, this copper wire becomes a current carrying conductor. Dia adalah satu conductor pembawa arus inside a magnetic field. Okay, these 2 magnets over here. Okay, there is a magnetic field. Magnetic field means inside here you can feel the effect of the magnet. Okay, so if one magnet is up here and one magnet is down here, there will be all these magnetic field lines lah. Okay, sama ada dia ke arah atas atau dia ke arah bawah. Not sure about it yet. But look at what happens to the copper wire. Okay, look at what happens to the copper wire here when we turn on the switch. Okay, tell me what you see. Okay, you'll find that the current, when we turn on the current, okay, what is the direction of the motion of the copper wire?
So cuba play it again.
Astaga. Okay. So now the copper wire is here, right? Okay. You can see my pen, right? Okay. Copper wire is here. Okay. Look at what happens when I turn on this one. Where does the copper wire go to? Okay. End of video. So when the current flows in a circuit, just now when the guy turned the switch on, where did the copper wire move to? To which direction?
To the right.
To the right. Okay. Shona, are you the only one in this class? Okay, it moves to the right. Now think about it. So now in this particular situation, okay, when we turn on the switch, the copper wire will move to the right. Okay. Can you predict what will happen if I reverse the direction? Means instead of flowing one way, I make the current flow another way. Do you think that the copper wire will also move to the right, or will it move to the left? What do you think?
Left.
Okay, it will probably move to the left. Okay, there is a principle, there's a principle behind this, but now I just want you to get the idea. When you change the direction of the current, okay, the direction of the motion also changes. Which means that ada beberapa faktor yang menyebabkan dia punya pergerakan. Sama ada dia bergerak ke kanan atau dia bergerak ke kiri. Same with your fan. Have you ever wondered why your fan only moves in a clockwise position? Is there a way to make the fan turn in a counterclockwise, anti-clockwise way? There is. One of the way is to change the direction of the current. Okay, change the direction of the current is one. Okay, what if you reverse the polarity of the magnet? Means, kalau katakan originally in this situation, okay, this was north and this was south, and then this one dia bergerak ke sini. What if I change the north to become south and I change the south to become north? Do you think it will be moving in the same direction, or do you think it will move in the other direction? Take a guess. Right or left? Awkward silence.
Left.
Okay. It may, but it will probably move to the left. So another thing that we need to think about, when we change the direction of the current, the direction of the motion also changes. Arah pergerakan dia akan berubah kalau kita ubah arah current, arah arus. Arah pergerakannya akan berubah kalau kita ubah kedudukan magnet. So let's say saya tukar utara dan selatan, bahkan saya kasih tukar bahkan, okay, the movement will be the opposite also. Okay, and this is the most important thing okay, if the direction of the magnetic field is parallel with the current, okay, which means instead of saya kasih baring begini, saya letak itu magnet begini dan saya letak itu conductor macam ini. same direction as the magnetic field. So the magnetic field lines begini. Okay, medan magnet yang warna hijau, dan saya letak the conductor in the same parallel direction. What will happen is it will not move. Okay, this is a very important thing that we need to start off with this lah. Okay, there are two things that actually affect the direction of motion. Okay, arah pergerakan kamu punya kipas, arah pergerakan kamu punya, this wire lah, is dependent on two things: the direction of the current and the direction of the polarity of the magnet. Okay, kutub magnet itu. And the third thing is you need to make sure that the magnetic field is not parallel with the current. Okay, so question number 1, is there a magnetic field in the region around the short copper wire before the current is switched on? Okay, this one, the answer will be no. Okay, let's not confuse this now, guys. I think we may need to go back a little bit to what you learned in Form 3, but I will answer this in a little while. Is there a magnetic field in the region around the short copper wire? Okay, before the current is switched on? No. Okay, there is a magnetic field around the magnetic magnet. Tetapi dalam conductor ini, okay, there is no magnetic field. Okay, name the two sources of magnetic fields in the region around the copper wire when the current flows. Number 1, sumber pertama adalah daripada the permanent magnet. The permanent magnet, there will always be a magnetic field. Okay, when you were back in Form 2, you learned that kalau ini adalah kutub utara, kutub selatan, the magnetic field is always this way. Okay, dari utara ke selatan. Dari utara ke selatan. Okay, and then the second one, is from the current carrying conductor itself. Okay, how many of you remember that when you were in Form, I think this is Form 2 lah, whenever there's a current flow, okay, whenever there is a arus yang mengalir, let's say for example this is a wire, okay, there is a current flow, whenever a wire, okay, has a current flow, actually there is going to be, the other way. It should be this way, yeah. Okay, there is always going to be a very temporary or very small magnetic field, okay, around any conductor. Okay, any current lah. Okay, any current carrying conductor will always produce a magnetic field. If you have forgotten this is the time to remember again. Okay, any wire, when the current flows through the wire, there will selagi ada arus mengalir. When you turn off, then the magnetic field also hilang. But when you turn the electricity on, okay, this wire will become a temporary magnet. And because it becomes a temporary magnet, okay, there will be a magnetic field. Okay, so this is the most important thing that you need to get your head around. Okay, and actually these are things that you have learned before. I'm just trying to make sure that you remember all this. Okay, number 3, from your observation, what makes the short copper wire move? Of course, it is the force. Okay, and there is a law that relates to these 3 things. As I said, force disebabkan oleh arus di dalam satu medan magnet. I repeat, the force happens because there is a current inside a magnetic field. Okay, and the law that relates to this, if you watched the video that I showed you yesterday, okay, it will be Fleming's left-hand rule. Okay, and so in order for us to understand what is Fleming's left-hand rule, let's take out our left hand. Left hand, everybody, I tell you, the amount of people that don't know the difference between the left hand and right hand, this is a millennial problem. Okay, tangan kiri, tangan kanan pun masih tidak kenal. Trust me. Okay, so this is the left-hand rule. Okay, the left-hand rule, you can look at this diagram is actually in your textbook. Okay, but let's not worry about this. Okay, the most important thing is all the 3, all the 3 fingers are perpendicular to one another. It's a 3-dimensional perpendicular, this one. This is perpendicular. This is perpendicular. Okay, and this is perpendicular. Okay, I've showed this. This and this. Okay, this and this are also perpendicular to one another. Okay, your hand needs to be in this position for this rule to work. Left hand, okay, I can still see some of you using your right hand. I don't care. I know how to see. Okay, left hand. So the best way to remember this, okay, I use this method lah. So I always call this FBI. Okay, FBI. F for force. Okay, B for magnetic field. Now the reason why I use the letter B is because if you do higher level physics, actually magnetic field, the symbol is B. Okay, so FB, and then the symbol for current is I. This one we've learned in the last chapter. So FBI. So this is the direction of the force. Okay, this is the direction of the magnetic field, and this is the direction of the current. Okay, and the direction of the magnetic field is always pointing from north to south. This is north and this is south. Okay, direction of the force, direction of magnetic field, north to south. Okay, and the direction of the current. Okay, depending on where the current flows. Okay, so have this in mind. We're going to learn how to use this today. Okay, so what is the relationship between the direction of the magnetic field, the current, and the force? Okay, force acting on the conductor. So fill in these blanks in your module. Okay, the top over here will be force. Okay, the one that is pointing from north to south, okay, is the magnetic field. Okay, and lastly, your third finger is electric current. Okay. Okay, in my experience, okay, I'm not sexist or anything, okay, but in my experience, I always find that somehow guys have a lesser problem doing this shape of the hand compared to girls. I don't know why. Okay, sorry, in my experience, always the girls got problem trying to move their fingers in a certain way. Okay, so but it's not impossible. Okay, I'm not saying that it's, oh, just because you're a girl you can't do it. No, I'm not saying that. But it's just I find that usually guys they automatically can do okay, and girls will be like, macam mana, somehow they will, you know that heart, that heart-shaped thing that saya sendiri pun tidak pandai buat. Yeah, sorry, but I know how to do this. Okay, so the relationship between all these three is that they are perpendicular. This is the most important thing. The force and the magnetic field are perpendicular. The magnetic field and the electric current are perpendicular. The electric current and the force are also perpendicular to one another. Well, sort of lah. Okay, yeah, I know my thumb is a bit weird. Okay, so explain why the wire does not move. You know, just now I gave you the situation. I said, what if the wire is in the same direction as the magnetic field? Okay, it is because the direction of the magnetic field is parallel to the direction of the current. Cannot move. Okay, the only way that this works is if all these three are perpendicular to one another. Okay, this is an amazing scientific discovery that is very hard to imagine until you see it come true. Okay, no one imagine that, oh, okay, kalau dia parallel kan dia tidak bergerak. Tetapi sekali kau kasih perpendicular, dia bergerak. Okay, so we have to really thank the scientific gods before us, okay, that thought about this. Okay, if the magnetic field and the current are in the same direction, okay, there is no force. Yeah, this doesn't work. Okay, dia akan mati. Same thing. Okay, the magnetic field and the force, the magnetic field and the electric current in the same direction, the force will not happen. So the most important thing is all these three must be perpendicular. Okay, think about this. What will happen okay, to the motion of the wire if you use stronger magnets? This is a very logical question, which I think all of you can answer. If you use a strong magnet, okay, just now in the case of our this one, so we had the one magnet here and another magnet, and then you had the copper wire. Okay, what if we change this magnet to a stronger magnet? What do you think will happen to the wire?
It pushes even further.
Okay, it will move even further. Very good. Because, you know, the stronger magnetic field will produce a stronger force. Logic, right? Stronger magnetic field will produce a stronger force. What about the current? Okay, we find that if you increase the current, you make the electric current bigger, okay, the force will also be bigger. And so it will move further. Okay, And so we find that these are the two most important factors yang menyebabkan kamu punya kipas ini boleh menjadi nombor 1, nombor 2, nombor 3. Think about it. Okay, when you press number 1, okay, it's weak. Sorry, can you see the fan? Okay. You all can hear. Sorry, you all can hear, right? Okay, so this is number 1. Okay, what if I press the number 3? Okay, we find that the fan moves faster. What are you changing? What are you changing when you press number 3? Anybody?
The current.
You are changing the electric current. You never thought about it, right? All you know is, oh, tukar pergi nombor 1, tukar pergi nombor 2. Tapi sebenarnya yang kau tidak faham, yang sebenarnya apa yang kamu sedang buat, what you are actually doing is you are changing the value of the current. Okay, how is the current value changed? We will not learn yet lah. Okay, that one is I think the next subtopic. The third subtopic. Okay, but it's a very important thing. When you press number 1, number 2, number 3, okay, when you know the aircon, the ting ting ting, the ting ting ting. Sorry, when you change the aircon, the speed of the fan of the aircon, what you're changing is you are changing the amount of current that is flowing inside the magnetic field. Because when you increase the current, you will increase the motion. We see this every day, Okay, we see this every day. We do this every day, and now, I hope that you are today years old when you realize that actually this is all physics. Okay, inside your fan there is a magnetic field. You can't really do much about the magnetic field in the fan. Yeah, okay, fine. If you want to do modification, okay, you can change the magnet into a bigger magnet but it is quite a big magnet inside the fan already. Okay, but what you can do is you can change the current. When you press number 1, you press number 2, press number 3. When you change the tombol, kalau kipas ceiling bahkan, you change the tombol 1, 2, 3, 4, 5. What you are doing is you are changing the electric current. Because when you make the electric current bigger, you create a bigger force. It moves faster. It's very, very important. So under what situation does a force act upon a current carrying conductor? Okay, you may need to copy this quickly. When a current carrying conductor is placed in a magnetic field, the conductor will experience a force. This is the basis of this subtopic. A force by a current carrying conductor in a magnetic field. Bila kamu ada satu wire, okay, and this is the current carrying conductor. Okay, this is the current carrying conductor. Inside the magnetic field, it will experience a force. Either it will move to the right or it will move to the left. Sekejap lagi, okay, I will teach you how to determine whether it's moving to the right or to the left. Okay, but the most important thing is the magnetic field must be perpendicular to the current. Okay, kalau saya ubah situasi ini, if let's say I say I make this copper wire in this direction, okay, instead of lying down like this, it will not move. Okay, it will not move. So these are the two important things that you need to know. When a current carrying conductor is inside magnetic field, it will experience a force. Dia akan tergerak. Okay, dia akan digerakkan. Okay, and the magnetic field is perpendicular to the current. Must be perpendicular to the current. Dia tidak boleh sama arah dengan current itu. Kalau dia sama arah, nothing will happen. Okay, this cannot. This can. Okay, very important thing. All right. Astaga. Okay, and so the direction of the force, okay, the direction of the force depends on two things: the direction of the current and the direction of the magnetic field. Okay, and so we want to learn this today. Yeah. All right. So take a look at this video. So if you take a look at this, so he's using his left hand. Everybody, he's using his left hand. Okay, using his left hand, he's showing to you that, okay, so this is the positive and this is the negative. So the current is flowing this way. Okay, so the conductor, this is the conductor. Okay, this is the conductor, so it's flowing this way. So he's putting his third finger like this. The magnet is pointing from north to south. So north is up and south is down. Okay, and so because of that, when you use Fleming's left hand rule, okay, follow this diagram. Okay, the current is flowing this way, pointing from north to south. So the direction of the force, you are expecting this conductor over here, okay, to move to the right. Okay, let's see whether it comes true.
Jari ni represent daya. Daya dia tunjuk mana? Berarti dia gerak sana. Kalau kita on. Betul lah.
Okay, sorry, could you hear the sound just now? Or was it echoey?
Can, sir.
Okay, all right. Wow, I love my mic. Okay, so let me show you once more lah. Okay.
Jari ni represent daya. Daya dia tunjuk mana? Berarti dia gerak sana. Kalau kita on. Betul lah.
Okay, so that is the basis of it. When you have the current carrying conductor FBI, okay, so this is north to south this way, current is flowing this way, current is flowing this way, and so we find that the force will move to that direction. Sorry, I just realized that I'm mirroring, so it will not work. Okay, I want to go back to what you were learning last time when you were in Form 2. Okay, this is all Form 2 stuff lah. Now, why is it that a wire, okay, why is it that a wire, there's a magnetic field? Sorry, how do we know the direction of the magnetic field? Okay, any single wire, because the wire is circular, okay, dia adalah berbentuk bulat bahkan. So the magnetic field, okay, is circular. Okay, and how you determine the magnetic field is by using the right hand grip rule. Okay, petua genggaman tangan kanan. So if your current is flowing from here to here, okay, we use our thumb, okay, to do this, and we find that the magnetic field is this way. Sorry. Yeah, the magnetic field is this way. So go back to Form 2 lah, okay? Go back to Form 2 and learn this. But anyway, the right hand grip rule teaches us this most important thing. Any wire, okay, any current carrying conductor, okay, will have a magnetic field around it. And the magnetic field is always circular. Okay, and these are the two most important notations that we see lah. Kalau dia bertanda X, okay, means the arah arus is memasuki. Okay, if you can see the screen with you, what you do is you point yourself towards the screen lah, and you'll find that these fingers will show you the direction of the magnetic field, and the magnetic field in this case is clockwise. Kalau dia adalah dot, okay, dot means keluar daripada kertas, so it will be coming in this direction towards me lah. Okay, so we find that the arah arus, the magnetic field punya arah is counterclockwise. Okay, opposite. Okay, so these things that you have learned when you're in Form 2, I'm just imbas kembali saja. Okay, the next one is this one lah. So this one is also something that I think you all learned in Form 2, but I'm not really sure. But this is an example that was shown to you lah. Shows another situation where a current carrying conductor experiences a force. Okay, same thing that happens here. The question is, we want to know what happens that menyebabkan this force to come up over here. Okay, and so a magnetic field, this is a video which I need you to watch first. Okay, so watch first lah. Let me know if the sound is like echoey.
The Lorenz Force is a phenomenon experienced by an electric current which is made up of negatively charged particles or electrons moving through a wire. Shown here as yellow particles.
Sorry, can you hear the video? Is it like very soft?
Electrons go from negative to positive. However, the convention is to think of electrical current as moving from positive to negative. So that's how we'll show it here using red particles. If it's not moving, a charged particle doesn't create any magnetic field. But when it moves, it generates a little magnetic field around it, shown by these green arrows. Flip the direction of the current, and you flip the direction in which the magnetic field circles around it. The magnetic field produced by the current will interact with another magnetic field, just the way two magnets repel or attract each other. Here's a horseshoe magnet with a north and south pole. The magnetic field always points from north to south, as shown by the blue lines. This wire is arranged in a kind of pendulum, so it can swing back and forth. Let's insert the horseshoe magnet into the setup and see what happens when electricity runs through the wire and creates a magnetic field around it. The pendulum swings in a different direction perpendicular to the horseshoe magnet's field and to the movement of the current. If we reverse the direction of the current, the magnetic field it generates will turn in the opposite direction, causing, in turn, the pendulum to swing in the opposite direction. Flipping the horseshoe magnet around to reverse the magnetic field around the pendulum will also cause the wire to swing in the opposite direction. The Lorenz force is what makes our electric motors work. Without this force, our modern world would be quite different.
Okay, so the most important thing is this. Actually, what causes the force is the interaction between two magnetic fields. Okay, this is the thing that we need to, so we are leveling up. Just now I said that, oh, okay, the force is actually caused by the permanent magnetic field and the current carrying conductor. Okay, but when you look deeper into it, actually a current carrying conductor, a wire that is bringing electricity, also has a magnetic field. So when these two, the magnetic fields, when they interact with one another, when they clash, okay, fine. When they clash, okay, or when they meet one another, they will produce the force. Okay, so the magnetic field from the permanent magnet, the one that north to south, interacts with the magnetic field from the current carrying conductor, from the wire. Okay, so when the interaction happens, the conductor will experience a force. Okay, because the two magnetic fields are combined, the two magnetic fields are clashing one another. Okay, so our next task is to figure out how to draw the pattern of the combined magnetic field. Okay, how does the combined magnetic field, okay, tell us which direction the force is moving? Okay, take a look at this diagram. Okay, so you have a current carrying conductor placed in a magnetic field. What is the direction of the force acting on the conductor? Okay, so the force on the current carrying conductor in the magnetic field is produced by the interaction between two magnetic fields. So the force on the current carrying conductor in a magnetic field, okay, is produced by the interaction between two magnetic fields, okay, as we said just now. Okay, and actually if you pay attention to this one, the name of the force is called a Lorenz force. Okay, this is actually not inside your syllabus okay, but it's called a Lorenz force probably because the guy who discovered this is called Lorenz. Okay, so there are two magnetic fields, as I said just now. The magnetic field from the electric current in the conductor, this one. Okay, the one yang just now dalam video tu yang berwarna hijau. Okay, plus the magnetic field from the permanent magnet, the one yang berwarna biru. Okay, and so this is what happens. When you have a current carrying conductor, remember this, dot means what? Dot means keluar. Okay, so if you use your right hand grip rule, keluar, you'll find that the direction of the magnetic field is anti-clockwise. Okay, yang ditandakan oleh yang warna hijau ini. Okay, so take a look at this now, people. When the magnetic field from the permanent magnet and the magnetic field from the electric carrying conductor, okay, when they combine, what will happen is it will produce a catapult or a resultant magnetic field, or we call this the Lorenz force. Okay, the Lorenz force. Think about it in this way. You remember last time when we were learning Bernoulli's principle? Okay, so Bernoulli's principle when we do the aerofoil kan. Okay, so di atas sini, the velocity is high, so the pressure is low. Di sini, what happens is the velocity is low, so the pressure is high. So high pressure to low pressure, there's a difference in pressure. Okay, so it will cause the aerofoil to move upwards. Okay, it works around that same principle. Take a look at this. The green color and the blue color magnetic fields are opposite to one another. Okay, so when you have two clashing magnetic fields, atas sini the magnetic field will become weak. Kan? Bawah sini, because they are in the same direction, the magnetic field will be strong. Okay? And so think about this. Where do you think the force will go? Will it go from the strong to the weak or from the weak to the strong? Bernoulli's principle, high pressure to low pressure. Okay, it will, hold on, let me just double check. Sekali tengok saya yang salah. FBI coming out. Yeah, correct. It will go from the strong to the weak. Okay, the force yang the force on this one akan daripada yang kuat kepada yang lemah. So we know that this wire is going to go upwards. Okay, and the difference in the magnetic fields, the difference in the strength of the magnetic fields will produce what we call the catapult, okay, or the resultant magnetic field. So a catapult field, is this in your module? Is a resultant field produced by the interaction between the magnetic field from a current carrying conductor and a magnetic field from a permanent magnet. So panjang. Okay, basically it's just a resultant magnetic field. It's like a resultant force lah. Kan? Resultant force is, you know, all the forces combined. Resultant magnetic field is, you know, when you have both the magnetic fields combined, okay, you will produce a resultant magnetic field. Okay, which the name for the resultant magnetic field is what we call a catapult field. Okay, do you know what's a catapult? A catapult is apa dalam bahasa Melayu tu? Plastic. Yeah, in Malay actually interestingly lah, okay, the word catapult dalam bahasa Melayu is called elastic. So kita panggil ini sebagai medan lastik. Okay, and how do we draw the catapult field? Okay, let's take a look at this. So this is how it would be. Okay, since the bottom area here becomes very strong, so the combined one will be very strong. Okay, all in one direction. Sini pula dia adalah lemah, so satu saja. And the force will always be from the strong magnetic field to the weak magnetic field. So this wire is going to go in this direction. Okay. Now, if we use Fleming's left-hand rule, okay, let's do it together. Fleming's left-hand rule. First of all, position your north to south. Okay, position your north to south, and then, so the north to south is, you know, follow the direction of the purple arrows lah. Okay, and then the current carrying conductor, right? The yellow color, this one is, since it's a dot, dot means dia sedang keluar menuju ke arah kamu. So north to south, okay, north to south, then dia keluar menuju ke arah kamu, okay, and so the force will be upwards. So there are two ways to determine the force. Okay, one is obviously the easier way, which is the Fleming's left-hand rule, and another way is to consider the combination of the magnetic fields. Bila dia bergabung, okay, dan di sini adalah opposite direction, it becomes weak. Here becomes strong. So when we draw out the magnetic field, strong itu kita letak banyak garis, yang weak itu biasanya kita letak satu garis saja. The force always travels from the strong to the weak. Just like Bernoulli's principle, high pressure to low pressure. Okay, so works pretty much the same way lah. So we call this the resultant force. All right, let's take a look at this. Sorry guys, I'm going to makan into your masa rehat sedikit lah. Okay, I need to finish this by today. So yeah. So diagram shows an arrangement to study the effect of a magnetic field on a copper rod carrying current. This is in your module, bahkan. Is this? Yeah, should be in your module. Okay, so on the diagram, mark and label with B, the direction of the magnetic field. Is it up to down or down to up?
U to S.
From U to S. Okay, so we will label from up to down, and then the B lah. Okay, now I want you to take a look at this. When the switch is closed, the copper rod moves along the copper rails in the diagram. Okay, now mark and label the direction of the current through the copper rod. Okay, so is the current flowing this way ke dalam atau this way keluar? Sini positive, guys. So is it going to go inwards or is it going to come outwards?
Outwards.
Okay, it's going to come outwards. Really? So bad. Come guys, let's follow. This is positive, right? So positive is going to go inwards bar. How do you get outwards? Okay, it's going to go inwards. Okay, it's going to go this way. Now, use Fleming's left hand rule. Everyone, take out your left hand now. Okay, do this together. I mean, do this on your own, but together. Tell me, is this rod going to move to the right or to the left? Use the left hand rule. Start with the B, north to south. Then,
To the right.
okay, it's going to go to the right. Marvin, are you using a left hand or right hand?
Left hand.
To the right, really? To the right.
To the left.
To the left. Sean, are you using a left hand or right hand?
Left lah.
Okay, it's going to go to the left. Okay, do it properly. North to south. Current is going inwards. Sorry. Yeah, current is going inwards. So the force is going to go to the left. Okay, yeah, this is a little bit weird. So usually when the SPM usually physics paper, the pemeriksa will always complain why all the students tiba-tiba dia akan menari doing this. Okay, but it's very normal. Okay, so once again, north to south, current is moving inside. Okay, so we have to position it like this. So we find that the force is actually going to the left. This needs a lot of practice, but very easily done. Okay, now that one is kalau kita menggunakan left hand Fleming rule. Okay, but we also need to be able to describe how it works by drawing the magnetic fields. Okay, so let's consider this. Now, magnetic field for permanent magnet, how will it look like? It will look like this. Sorry, tak apalah, saya jawab sendiri lah. Okay, it will look like this lah. Okay, the always flowing from north to south. Now, current carrying conductor. Guys, X means masuk ke dalam. X means masuk ke dalam means use your right hand grip rule. Okay, and you will be able to draw circular magnetic fields. The only problem is we need to know whether it's going clockwise or anti-clockwise. How do we determine this? We determine this by using the right hand grip rule. Okay, this is the right hand grip rule. Okay, every day kamu buat begini kan, point ini nilai ni. Okay, the right hand grip rule. So the thumb tells you which direction to point the current. So X maksudnya dia masuk ke dalam kertas. So, sorry, masuk ke dalam kertas. So, if you take a look at it, okay, kalau dia masuk ke dalam kertas kan like this, so you find that the fingers show you the direction of the magnetic field, which is clockwise. Okay, this is exactly what will happen. So now the thing is we need to combine both together. Okay. So sorry I need to go very fast. So if you like missed out on this nanti kau tengok video dan kau sambung balik salin balik. Okay, so let's draw the combination. Okay, so we combine these two together. Okay, and then we find that we find this interaction happening. Okay, look at this side of the conductor. Okay, same direction makan. Okay, the blue and the green are same direction. So over here, the magnetic fields will be stronger or weaker? It will be stronger. Over here, the magnetic fields are opposite to one another. It will be weaker. Okay, so my question is, where is the direction of the force? To the left, to the right, to the up, to the down?
To the left.
Okay, it will go from the stronger to the weaker. Okay, same direction magnetic fields will produce a stronger this one. If it is weak, then it will be this one lah. Okay. So what can we say about the strength of the magnetic field? If the combined magnetic fields are same direction, it will be strong magnetic field. If it is in the opposite direction, it will be weak magnetic field. Okay, and so the strong will be here. Okay, astaga. Okay, and the weak will be here. Okay, and just as you said just now, we will find that the force will move to the left. Okay, so this is an example of a drawing that you can, this one. Okay, so when you draw the combination, this is what the catapult field will look like. Yang strong, kita lukis banyak garis yang berdekatan. Okay, of course you need to draw this the direction lah. Okay, yang weak biasanya kita lukis satu saja just to menandakan the weak. Okay, the weak magnetic field, and we finally draw the force. So two ways to determine the direction of the force. Okay, one is if we consider the magnetic fields. Another way is when we do Fleming's left-hand rule. We can still use Fleming's left-hand rule for this. Hold on. Okay, sorry. Yeah, we can still use Fleming's left-hand rule for this. Think about this. Okay, so north to south. North is on top, south is at the bottom. X means dia masuk ke dalam. So point it this way. Astaga, point it this way. Okay, so north to south, X is masuk ke dalam screen. Okay, masuk ke dalam screen, masuk ke dalam kertas. X lah, X is masuk ke dalam. So the force will be to the left. Okay, left hand people, left hand. Okay, left hand. All right. So what is a catapult field? Oh, I think I can finish this soon. Okay, so a catapult field is a non-uniform resultant magnetic field. So in the case that we were seeing just now, this is the catapult field that we are supposed to see lah. Okay, if this is north and this is south and this is masuk ke dalam. So catapult field usually, as I said just now, the stronger regions will have more lines. The weaker regions maybe one or two lines, but you know, dia memang berjarak-jarak. The stronger regions are near to one another. Okay, so in this case, the resultant force will be towards the left. Okay, name the rule to determine the direction of the force. It will be Fleming's left-hand rule. So again, as I said lah, two ways to determine the direction of the force. Satu, kita pertimbangkan the two magnetic fields. Okay, strong magnetic field to weak magnetic field, combined magnetic field. Okay, the second way is by using Fleming's left-hand rule, which is the more popular way, especially in the situation where you don't know where is the direction of the magnetic field. Okay, although you need to do both lah. Okay, so take a look at this lah. This is an example of example of the guy who has twisted his hand just to show you where is the direction of the force. Okay, the direction of the force is here. So coming back to the same question, what will happen if your rheostat is adjusted until its resistance decreases? Do you think what will happen to the motion of the copper rod? Will it move further or will it not move so far?
It moves further.
Further.
Why? Why does it move further?
When resistance decreases, the current increases.
Okay. When the resistance decreases, the current will increase. This is something we learned in chapter 3. Okay. Kurang rintangan, besarlah aliran arus. Sama lah macam, it's the same as river flowing in water lah. If there's not so many stones in the water, in the river, then the water will be able to flow much faster. Okay, so when you when you decrease the resistance, you increase the current. And we've said just now, when you increase the current, the force will be much bigger. Okay, and the copper rod will move further. Now, what will happen if the battery is replaced by the AC supply? Okay, so just now we saw the situation is battery. And even in the video that we saw just now, okay, it's battery. But now instead of using battery, I use an AC power supply. Okay, AC power supply means sekejap positif, sekejap negatif, sekejap positif, sekejap negatif, dia berubah-ubah. Okay, what do you think will happen to the motion of the rod? Anybody want to try?
You swing back left and right.
Okay, there are two possible situations. Both of you are also correct. Okay, number one, because the direction of the AC current changes, dia sekejap di bawah positif, sekejap di atas positif. So one possible explanation could be it will change direction. It will vibrate lah. Dia akan bergerak ulang-alik. Okay. Another possible one will be kalau dia terlampau ulang-alik, bahkan it will look like it's not even moving at all. Okay, it will look like it's not even moving at all, which is a very common thing that happens to the fan. Okay, if the fan, so electricity yang sampai ke tempat kita adalah alternating current lah, definitely. Okay, so yang kita nampak di plug semua bahkan adalah alternating current. So there is something inside the fan that changes the alternating current to a direct current. Otherwise, what's going to happen to the fan? The fan is going to go back and forth. It's not going to do its job properly. They can, mengulang-alik like this. Then what's the point of the fan, right? Okay. Or even worse, if the current becomes so big that dia ulang-alik kan, it's going to look like it's not even moving at all. Sebenarnya dia vibrating lah. Okay, but it's going to look like it's not moving, which is a very common fan problem. Sometimes kan if you overwork the fan or if you use the fan too much kan, one day the fan spoil kan, and you say, oh, saya boleh kasih hidup, tetapi dia macam ni dia punya pergerakan. Then you know that something in there has made the AC, dia tidak dapat menukarkan AC kepada DC. Cannot change the alternating current to direct current. Okay, that's the main problem lah. Okay, so it's a motor problem lah, so we say that. So it can be one, it can be both. Okay, so both of you are not wrong. Mungkin dia akan, it will swing back and forth, like dia akan pergi sini, or it will just vibrate, or it will vibrate sampai kau nampak macam dia tidak bergerak. Okay, it vibrates so fast until it looks like, it's not moving at all. Okay? Now, dua kerja untuk kamu pada hari ini ya. Number one is this. I want you to memorize this explanation. This explanation is a 4-sentence explanation, which every year I always tell my students to memorize this. Okay? Commit this to memory. Besok kita ada kelas kah? Oh, okay, Thursday. So in the next class, I will ask you to recite this. Somehow I will figure out the way for you to send me this one. When the switch is on, the current flows through the short copper wire, produce a magnetic field. The interaction between the magnetic field produced by the current carrying and the magnetic field of the permanent conductor magnet occurred. Permanent magnet occurred. C. The interaction between the two magnetic fields produces a resultant force on the conductor, which we know as the Lorenz force. You don't have to know this, but it's just extra information lah. Okay, it's called the Lorenz force. The interaction produces the Lorenz force. Okay, and because of that, the short copper rod moves. I want you to add a fifth one. The direction of motion is determined by what? How do we determine the direction of the motion?
Fleming's left hand rule.
Okay, Fleming's left hand rule. Left rule. Okay, Fleming's left hand rule. 5 very short points, everybody. I want you to memorize this, commit this into memory, and I will test this in your next class. Okay, that is work number 1. Work number 2 is, this is a very simple work. Okay, I want you to do exercise 1 in page 128. You know there are 2 questions there underneath number 10. Okay, so draw the magnetic field and using the Fleming's left hand rule, draw the catapult field and state the direction, just like I showed you in the slide just now. Okay, this one has to be handed in today. Please hand in the Telegram group. So what you do, in the Telegram homework channel. So what you do is you just take a photo, don't need to PDF. Okay, tak perlu PDF. Kamu lukis-lukis bila kamu sudah siap, just take a photo of the exercise and send it into the channel by leaving a comment. Okay, so kamu tekan di sana, leave a comment, and then I will put the broadcast up later lah. Okay, go into the channel, press leave a comment, and then submit your work over there.